Hey guys, my name's Jack Stewart, and this is my Physics 2212 Lab 4 on circuits and capacitors. This is my fourth time recording it because I keep running out of time, so let's hop right into it. Introduction. So on the left, the purpose of this lab, we're going to be using the principles of energy conservation and current conservation. And in using that, we're going to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and finally examine the behaviors of ohmic resistors and capacitors. And we're going to be using an online PhET lab provided to us to actually model circuits. Some of the fundamental principles of this lab and topics we will cover are the conservation of energy, Kirchhoff's circuit laws, and capacitance. So let's hop right into what we were going to do for the lab. On the left, we were given a picture model in the instructions. And then on the right, we used the PhET lab I talked about to actually build it. And as you can see in the actual building, we have two batteries on the left. We've got an ammeter on the top and the bottom, and then two resistors, one with 47 ohms of resistance and one with 100 ohms. And then we have wire connecting it all. And then as you can also see on the right, there's a dog in there. It's not actually affecting the experiment, but I wanted to include it because I thought it was cool, and I think it's cool you can include a dog. One of the things you'll notice is that both the top and bottom ammeter read 0.12 amps, and that is I1 equal to I2 due to the node rule. So for the second part of the lab, we had a similar setup. I didn't have to affect it too much. But on the left side, we still have the two batteries. Now we only have one ammeter. And then at the bottom, we added a voltmeter to measure the voltage flowing through the batteries. And as you can see on the left picture, the actual circuit is broken down by letter from A to B, B to C, all the way through H. And so we're going to use that in the next part. On the next part, we were asked to measure the potential difference across each section. And when we mapped it, it looked like this. It's at its highest between B and C, and then it falls back down when it connects back through the ammeter. The next part, what we were instructed to do is build a setup with a light bulb. And as you can see on the left and right, the left side has a battery and the right side does not. That is the only difference in the two. They both have a capacitor on the right side. And what you can't see in the pictures, because they're not videos or GIFs, is that in both, the battery lit up very brightly and then went dim quickly. Our findings from that, we measured the potential difference over time, and we used this formula given to us on the left. We were able to map it over time using the natural log, and we got a line, a straight line to mention, with a negative slope of 0.17. And then we, of course, want to talk about possible errors in this lab. It was a struggle to adjust to the online model. Not too difficult, but it took some time to learn how to use it. But there are potentially no errors, at least that I could tell, because this was an online resource and we were able to use this in a world with ideal conditions. We'll talk a little bit more about that in a minute. The two reflection questions we were asked: what if we were doing the lab in real life and use an actual ammeter instead of an ideal simulated ammeter? What difference about a real ammeter, and how would it affect the circuits you hooked it up to? It would not be as accurate due to, as I talked in the last slide, we didn't have to deal with human error as much. We did have to still deal with human error, but in a lab, we would have much more of a problem messing it up. But the other thing messing it up would be there would be resistance in the ammeter, which would affect our readings. And then secondly, we were asked, what if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the current? How quickly would our ideal model predict the capacitor to reach full charge? It would reach it very quickly, almost immediately. Without the resistor, the battery would charge much, much quicker because there would be no resistor to resist it. Thank you very much. I hope you learned something.